and so I missed all of the exchanges with the working groups and so forth. But how good does it work so far? Can people split into groups and be productive
Yeah,
despite the condition?
a lot of really interesting projects. I think finding team is maybe harder online when you don't have lunch and other occasion to just meet people. But I think having you know folks that work on a different time schedule, that kind of helps as well. So you wake up in the morning and someone in Europe has done work, or and some people have been really good at like staying up late and watching lectures, even though it's like midnight for them. So we're lucky at we use the usual tools, so it's Zoom and Slack, and we're just lucky that we have a lot of really, really good, incredible participants. So I think it's going well.
Oh, that's great. And and so last year there were quite a few participants that were coming from Université Laval and also a few from Vermont and then people from elsewhere. Does it look the same this year, or it's more spread out given that it's virtual? It makes it easier for someone to attend from.
I
Yeah,
think it's a little bit more spread out this year.
yeah, for sure. I mean, we have like one or two from Sherbrooke, maybe one or two from Laval, and then I want to say like three from Vermont. But and I think it's a lot more spread out, which is great.
Mhm.
And how does it is it sorry how is it distributed among the different um, sciences?
Hmm.
Is people coming mostly from physics, or you have people from everywhere,
No,
from all over the place?
no, we actually try to pick participants so that we have a good diversity of backgrounds. And so I don't know if I didn't look at physics. There's a, but it's pretty diverse in general. That's what we aim for.
Yeah, that's a good question. I could do a poll if I knew how to do polls. Let's see.
I mean, you and then you just write disciplines, the answers.
It's very weird that it's through a web interface, though, setting up a new
Title of the
Yeah.
question.
Zoom.
Wait, here?
This is for the question. This is the title of the poll.
Okay.
You want me to name disciplines?
Yeah, I'm like, I don't know.
Right, physics, biology, ecology, mathematics,
Social.
social sciences. Put them together. There's a lot of medicine. Well, a few medicine,
Industry.
industry, computer science.
Yeah. What are we forgetting, guys?
I'll put art.
Stats
Okay.
with
And I'll-
math.
Oh, math.
Yeah, I have math. I don't have. Yeah, I'll put math and stats together.
That's a shame.
I know how you feel about that.
Then I'll put. I mean, I feel like putting social sciences all together like that is also a shame.
Well, we don't have time to like.
Okay, it's safe. And then does that
Wait, now let's see if it's there. I've never done a poll before, so this is interesting.
polling? Yeah, throw it, launch poll. Okay,
Okay, there's a poll now. Did you guys see that? Okay.
it's happening. It's happening.
Whoa.
Wow.
I have two. I've studied two disciplines. So who am I?
Oh, you have to make a decision. That's hard.
Sophie's choice right now.
Computer science is quite a few. Yeah, biology and ecology. I maybe should have like kept them together. Urban sciences. Ooh, that's a good one. I didn't put engineering. That should have been in there. Engineers can use others, I guess.
Maybe it should have been the check box instead of choice.
You have a bias, eh? Coming
Oh
from
yeah, for sure.
putting everything in other.
I
Other.
feel like complex systems would have been a good category.
But that's too broad.
See, this is hard.
Yeah.
Okay, so I feel like the people.
That's the all of the above.
Yeah.
Okay, so we have mostly math and
Do we
science.
begin? Okay.
Oh no, computer science.
Computer science.
Okay.
Jean-Gabriel,
There's an
what did
ability
you
to
put?
share the poll too.
Oh,
after
can I
you
share it?
stop
What
it.
do I do?
What, do you all
I-
see the results or just us?
I think you need to share them again.
How?
All of this is mystery to
There's
me.
not a
Maybe
button.
we have to end it and then share. Yeah,
Yeah.
share
Oh,
results.
okay, I see.
There you go. Oops. So which one was at 22%?
Well, computer science is half of the
Mathematics and
answers.
statistics.
I mean a quarter.
No, yeah.
But yeah, Jean-Gab, what did you put?
I couldn't enter it as a co-host.
Oh,
Uh,
right.
I guess I would have put physics just for old times sake.
Feeling sentimental. Okay.
But see, biology plus ecology, if I had
Oh.
combined them, I would have gotten a 9 there too.
That's a good point. Okay, done.
Okay, should we get started and we let people in, we can let the latecomers in when they join?
Mhm.
Yep.
Okay.
Sure.
Antoine, do you want to introduce our speaker?
Yeah, sure. Okay, so it's a great pleasure to introduce this afternoon's. Are you recording? Doesn't say so right
yeah.
now.
Yeah.
Yes.
On mine, it does. Okay, sorry.
Oh, wait. Let me make you a co-host.
Maybe it's probably because that's why I don't see it. Okay, good. Okay, so I was just saying it's a great pleasure to introduce this afternoon's speaker, Dominique Gravel. So Dominique holds a Canada Research Chair in Integrative Biology and is a full professor at the Department of Biology at the University of Sherbrooke. So just to give you an idea, Sherbrooke is in the southern part of Quebec, and I didn't look at the map, but more or less it's midway between Quebec City and Burlington, more or less.
Pretty much, yeah. Exactly.
Pretty much. So yeah, so we met Dominique last year, thanks to Marie-France Gébry, who's co-organizing this workshop. And we are delighted to have welcomed him again this year. I'd say what makes Dominique such a great fit for Canoe is probably how close his approach to science is to the kind of philosophy that we want to promote here. So you will see that he has very broad research interest. I'm thinking of whether it's the global marine fish food web, or the ecosystem of a very specific island in the Arctic. So these are the kinds of systems that he studies, but he's also interested in the methods themselves. So as a result, I've been in meetings with Dominique where we talk as much about the life cycle of lemmings and talk about the Lyapunov function that one of his students used to characterize the stability of one feeding dynamic on one given island. So whenever you're ready, Dominique, floor is yours.
That's good. Thanks, Antoine. Glad to see you, Antoine. By the way, nice haircut.
Thank you.
I don't remember who was making a joke last year that every time we see you, you have a different beard and a different haircut. So it's good to underline it. Hold on, I'm just gonna try to put my slide full screen. Function F5. Okay. Can you confirm me that you see my slides?
Yes,
Yeah.
looking good.
And if I do change them, you see them changing as well?
Try that again.
Sure.
Yeah, that works. Okay.
Yes.
Yeah.
So I'm not gonna do like Sam did, making half of his talk and not showing his slides. Actually, I wasn't sure what to present today. It's a bit bizarre because last year when I was there, it was very exciting to attend to the first talks for 2 days and then present my own. So I was able to prepare the content and just to tweak or adjust the content to the audience and the type of talks. But this year, it's remote. I've been super busy for the past few days, so I missed some of the first lectures, and so I wasn't sure about what to present. But then I decided that I may just try something that is completely new. New because the research that I'll present, at least 2/3 of it is still ongoing. It's one single project that I'm running, and it's ongoing. We're still acquiring results at the moment, but I thought it would be great just to share it with you, and perhaps have some feedback on that research. I also think it's a good and an interesting topic to introduce complex systems and what they are the greatest for, which is collaboration among different fields of science, where you can share ideas and achieve much more with that. So part of the research that I'm gonna show you is some work that I've started to do with Alan Cohen from the med school, and Thomas Phillip, also from the med school. We've been starting to exchange something like 3 years ago. So Alan is a former ecologist, but now he's a full faculty professor at the med school, and he studies aging. And ever since he did his PhD in ecology, he was interested by quantitative methods. And in ecology in particular, we have a wide range of methods that we use on a regular basis to deal with the complexity of the data we have to handle. And so he got inspired by some of the methods, and he contacted me, as I said, about 3 years ago, because by studying aging, he was interested in using one of the methods that we developed to study the covariation among abundances and presence of different species. You have to know that in ecological systems, most often the type of data that we deal with is highly multidimensional. It's very rare that we study problems with univariate measures. You know, often when you study a community, you have a bunch of species and you have to make sense of that highly dimensional data. And that inspired us to develop some methods for the analysis of species distribution and abundance. And for some reason, Alan learned about that method that we were using and thought that it would be great to study the process of aging as well. And so we started collaboration at that time. And about 2 years ago, we submitted a grant to a program that is called Audace in Quebec, which specifically aims at funding research projects that are highly high risk, potentially high return, um, and projects that are interdisciplinary. And so we decided to submit there a project where we would compare the structure and dynamics of ecological systems to the structure and dynamics of immune systems, so that we could better understand how the human body react to infections and inflammation and things like that. So I'll show you a bit about that work today and some of the directions that we're taking. And I could go for an hour and a half, but I think at some point it would be great as well just to take breaks and ask yourself questions. So I hope we could eventually have a more interactive session and not just a long lecture from the beginning to the end. So I could just start by very briefly talking a bit about myself, what I've been doing, and where I'm going, and how I ended up doing that kind of work. So here you have a picture of Mont Mégantic, taken in the fall in Quebec. It's obvious on that picture that as you go up the slope, you quit the sugar maple deciduous type of forest that is currently orange on the picture. And then you enter the boreal type of forest, which is in green, because it keeps those trees keep their leaves during the winter. This transition you see is pretty sharp. In a few meters of elevation, you have a very abrupt transition from one forest type to another one. And these are two completely different forest types. And so as a biologist and ecologist, as a modeler, I've been interested by that transition for years. Given the the ongoing climate change, the main research question that I have is, how is this tree line reacting to warming? How fast will the maple trees climb up the hills and eventually colonize those boreal forests that you have at the top? And it could, as the climate warms, the response could be of different types. We know for sure that in about 100 years from now, or no, if we go even further, let's say in 1,000 years from now, once the climate will stabilize, the vegetation will respond, and eventually you're going to have forest dominated by maple all over this mountain. But in between, we don't know much what's going to happen. Is it going to be something that will be very gradual, so the climate warms and slowly but surely the maple trees are climbing up the hill? Or is it something that's going to, nothing's going to happen for a while, and then all of a sudden, bam, the forest will change very abruptly from one forest type to another one? Or is there hysteresis, so that actually if we go forward in time and look at this picture again in 1,000 years from now, maybe perhaps we could still have exactly the same tree line because we have alternative stable states that are preventing the maples to climb forward, upward this mountain. So I've been working on this problem for several years, and it got me to think and get in touch with the literature and complex systems that deal with what people call, well, there are a few keywords that are interesting and relevant, and then you're going to hear about today, and you'll see quite often. You'll hear about early warning signs, critical transitions, abrupt changes, critical slowing down. These are all terms that are used to describe the change and the types of dynamics that we see for such systems. So I've been interested by that literature for a while, and I try to apply some of the theory that has been developed for a broad range of complex systems, and I try to apply them to this one in particular. We also, I mean, in several aspects of nature, we do see very sudden changes happening. So you have a picture of cod fisheries. We know what happened in the 90s. So in the 80s, there were still very, very abundant stocks of cods, and fisheries were going on and were very successful. And all of a sudden, by the late 1980s, the stocks just very abruptly collapsed. And then the government reacted to this sudden change in the marine ecosystem. The response was performed after the observation of a collapse of the stocks, and it would have been great to be able to anticipate that if there were signs that could allow governmental agencies to prevent this to happen and react prior to the change and not in reaction to the change. You see this in different aspects of life. It's not only with biological systems that you do see very abrupt change and people looking for statistical signatures or observation that could help us anticipate this type of system dynamics. I mean, the financial crisis that happened in 2008, a lot of people post-hoc looked for if there were any signs of that were announcing this potential crisis, so that people could have hacked before. And now today, I think we're slightly better equipped to prevent those things to happen, although we're not completely there yet. Another example where we expect abrupt changes to happen is in climate itself. We have projections telling us that the average air temperature will increase by 4 to 5 degrees within the next 100 years if nothing change. But we don't know that much if this change will happen very slowly or if it may happen very abruptly. And so people studying, for instance, the dynamics of ice in the Arctic are looking for those early warning signs, trying to anticipate when a massive climate change could occur. And my collaboration with Alan was also motivated by the same question. In his case, it's about aging. So with aging, we know that a lot of things are happening. Some of them are very gradual, but some of them are happening very, very suddenly. And so it'd be great if we had measures that we could take on the human body to anticipate those very abrupt change in the functioning of the body and of the health of people. So that's basically the question that I have today and that we're going to discuss all together. Can we anticipate the sudden collapse of such complex systems? There's a variety of complex systems, but the ones that I talked about today all to a certain extent consider that they are made of they could be described as networks where you have elements that are interacting together and that are giving rise to emergent properties. This is quite archetypical of the definition of complex system. Just before I enter the theory, I just want to broadly go through some very basic concepts, so at least we could start from a common understanding of those concepts and use the words properly. I figure that most of you heard and many of you probably use the word resilience in your research on a regular basis. Um, and you very likely found that the word resilience is used in so many different ways. But in quantitative science, it's been defined, and in the science of system dynamics, it's been defined quite a while ago, and it has a fairly restricted and unique definition that is important to be precise. So the resilience, it has two components. First, a system is said resilient when it's able to go back at its original state once a disturbance happened. This concept is often illustrated with the ball and the cup illustration that you have here on the slide. So at the top you have two systems, one that is called highly resilient, and the other one is as low resilience. But the two of them are resilience in the sense that in any case, if there's a perturbation that is moving the ball away from the bottom of the cup, it will go back to that equilibrium. The amount of resilience you have is, in this analogy, corresponding basically to the shape of the cup. So the wider is the cup, or if you have a plate, for instance, you're going to have very low resilience because it's going to take a lot of time before the ball goes back to the equilibrium. It's going to move a lot around before it eventually settles to the center. But in both cases, as I said, there's an attractor. If instead you're taking a coffee cup or champagne glass, for instance, you have a very steep walls, and the cup will the ball will very quickly go back to the center. And so this system would be called highly resilient and with low resilience. Resilience is often confounded with resistance, which is something that is slightly different. So for a given amount of perturbation, some systems will experience a very large amount of change in their state, and other systems will have a very small amount of change. So for instance, if we think about climate change and we just warm the climate by 1 degree, in some biological systems, you won't see any difference. So if you warm the temperature by 1 degree on average in the boreal forest, for instance, I'm pretty sure that it's going to stay a boreal forest. So in that sense, it has a fairly high resistance. Other systems, however, will experience a very massive change in their state and their dynamics following the similar amount of perturbation. So in this case, we will say that the system has low resistance. So if you go in the Arctic, for instance, which Antoine referred to, a system that I study with collaborators, when we look at food webs over there, we know that just a very small amount of warming could have a dramatic impact, especially at some locations, because right now the Arctic is dominated by herbaceous plants. But if you just warm the temperature by a slight amount, 1 degree, for instance, you may have bushes that are entering the landscape, and these will generate a three-dimensional structure in the landscape, and this will have a huge impact on the ability of different animal species to hide, to find food, to find shelter in the winter, and it will also impact the distribution of snow and so on. And so just a small amount of temperature change could have a huge impact on the dynamics and the state of that system. So in this case, we will say that it has very low resistance. And I said earlier that you also have early warning signs. So what I will call an early warning sign is a property, a statistical property of a system. Usually it's computed based on the dynamics of the system, but sometimes it's also computed or extracted from the spatial structure that you have of a given system. It often happen with vegetation. People are using the spatial signature of that system to evaluate early warning signs. So these are, we look for them, we try to find them to indicate or to anticipate a major change in the state of the system. And the theory that I will refer to and what will follow, it happens because of a critical slowing down. So the idea of a critical slowing down is basically as you have a permanent change in the system, let's say warming, that is happening, then the system progressively changes and its resilience may decrease before it eventually reach another state. In my example that I'm studying with the distribution of temperate trees and of boreal forest, I look for a critical slowing down at transition between the two type of ecosystem. So the temperate forest is pretty stable, the boreal forest is pretty stable, but what I expect is that at the tree line, at the border of the two distributions, I expect to find a significant decrease in the resilience of the forest ecosystem, which eventually may lead to or may be indicated by early warning signs. So before I enter the univariate theory and I explain where these come from, I may just open you to questions. Does anyone have questions so far or reactions?
Masa, do you have a question?
Yeah, maybe if I can rephrase the question was whether, so the question was about robustness. So
Yeah, if resilience and robustness are the same or different concepts.
That's a good question. I rarely see robustness. I would need some context to say if it's the same or not. I will come with a more precise definition or a more mathematical definition of resilience and what will follow, perhaps that will allow you to answer your questions. I feel that robustness may be a mixture of resilience and resistance. People often confound the two or use these terms interchangeably.
And Alice has a question, I think.
Yeah, my question was about the last bit with resilience, where you mentioned that you have a rate of return to some initial state, and if your change is large enough, it might not return to that at all. Is that in any way related to thinking of systems as dynamical systems with different fixed points and basins of attractions, and kind of the rate at which within the basin of attraction I arrive at a fixed point?
Yeah, exactly. And so, this picture is pretty clear. The figure that you have on the left and on the right for A and B. In both cases, you do have one attractor on the left, and if you push the ball far enough, then you may eventually reach a new attractor. I don't want to go too much into details today. I'm not going to talk about alternative stable states, but definitely a system that has alternative stable state as very low, if not no resilience, because if the disturbance is large enough, then it just goes to another attractor. But then there's the thing is that you need to be then after a little more precise, because the system may be locally stable, or by the way, resilience and stability often go together. So the example here is a good one. It's locally stable because if the disturbance is not too big, then it goes back to the equilibrium, but it's not globally stable because if the disturbance is very important, then it may switch to another attractor.
Thanks.
That's good. Okay, so now I'll move I'll move slowly into the theory, and eventually we will get to a real case with data analysis with the human body, which is completely out of my field, and well, we'll see. This idea of resilience was developed having in mind a highly deterministic view of the world. So basically here you have a time series, you have the state of your system on the y-axis, and you may have at some point a perturbation. So the system moves away from the equilibrium being represented obviously by the dotted line. And then the system will eventually go back to this equilibrium. And the rate at which it goes back is the measure that we would use to characterize the amount of resilience the system has. But this is essentially theoretical because such systems are never like that, or very rarely like that in nature, especially biological systems like I study in ecology. Often what we do have are time series that look like this. And so you have an average, which you may want to qualify it as an attractor, but you just have an average and the system constantly moves away from that average because it's constantly disturbed by some externality, like the climate could change, you can have another species getting in, you may have wildfires. I mean, a bunch of things are constantly disturbing the system. And so in this case, in this situation, you need a completely different definition, or at least mathematical definition of in order to be able to quantify the resilience, because there's no way with a time series like that you can compute the rate at which the system goes back to equilibrium if you cannot precisely quantify the perturbations. And so in what will follow, we'll describe another conceptual representation of resilience, which was proposed by Tony Ives, who's an ecologist. It was proposed in the mid 90s. He called this stochastic resilience. And so basically from this time series, you can compute the total variability that you have in the state of your system. So you just compute the variance of the time series over time. And what we will look at is the amount of variance that is caused by externalities and the amount of variance that is caused by the home dynamics, the internal dynamics of the system. And so according to Ives, in a system like that, a proper definition of resilience would be the ratio of the variability that you have in population density. So all of the variability that you have in that time series by divided by the variability that is driven only by population growth rates. And so if you have very low variability that is driven by population growth rates, you have a system that is highly resilient. And if you have a larger variability that is generated by the population dynamics, then you have a system that has very low resilience. You'll see the match with the prior definition of resilience in the upcoming slides. So if we try to represent the time dynamics of such a system in a deterministic one, so 2 slides above, you have the state of the system X at times t plus delta t, being a function of the state at the previous time step and an exponent where the lambda that you have here is the rate of convergence to the equilibrium. So this equation will very much correspond to the type of dynamics you observed in the first figure that I shown. In a stochastic system, the representation is slightly different. What we will explore is the one that you find at the bottom. So we will basically look at a autoregression model where the state of the system at times t plus delta t is a function of an intercept, its state, a linear function of its state at previous time step and some externality here. So epsilon corresponds to just noise that is added to the system on a regular basis. And so basically what we're going to look at is conceptually is a figure like this one, where you express the state of the system at times, at some time in the future and against some time in the past. And there are two quantities that are highly important in this figure. So first you have a trend here, the dotted line, that is called autocorrelation. So that describes you how fast or how slow the system's response and change to its previous state. It's a bit counterintuitive. If the line falls very close to the one-to-one line, that means that the system is not changing much from time to time. So in that sense, if you have a slope that is close to 1, that means the system has very low resilience, because it's basically going to stay the same from one time step to the other one. If the slope is very close to 0, then you have a system that is highly resilient, because that means it's going to go back very, very quickly after a perturbation happens. The other quantity that is important here that you do find in the equation here is the epsilon. So the residual that you have from that regression model, it's telling you about how much disturbance you have, how much perturbations are happening and are driving the dynamics and the variability in that system. So of course, the larger they are, the more stochastic the system will be. This epsilon, or this residual variation, could also be interpreted as a measure of resistance instead of the measure of resilience. So we have this equation at the top that is describing the dynamics of our system. And what we'll do now is that we're going to take the variance on both sides of that equation, and just playing a bit with the terms, you obtain the equation at the bottom, which tells us that the variance of the state of the system, once we reach a stationary distribution, which means that there's no major change in the state of the distribution, in the moments of the distribution over time. So this total variance is equal to the variance of the externalities divided by 1 minus the regression coefficient, so the slope of the autoregressive model that you had before. This could be interpreted basically in terms of resistance and resilience, the concepts that I defined before. So you have the total variance of the system above. You have the measure of stochastic resilience, which is 1 divided by 1 minus the regression coefficient. And so when and here there's some twists, and you need to reverse your thinking. The smaller is this quantity, the more stable the system will be. The larger this quantity, the less resilient it will be. Sorry, I said stable, I mean resilience. So if we think about this regression again, if the slope is close to 1, there will be very strong temporal autocorrelation, which means that the system will pretty much stay the same. I mean, it's not going to react to its state, and it's just going to accumulate perturbations, and that will lead to a lot of variability over time. And so in this situation where alpha 1 is close to 1, that means that the denominator will be close to 0, and this quantity here will be very large, which means that the resilience is low. Rather, if the coefficient is close to 0, then you're going to have a measure that will be very close to 1, which indicates that the system has high resilience. And then you also have the variance of externalities. So all of this together led people to develop criteria for early warning signs. So presumably what we are interested in is using time series to infer the amount of resilience that you have in a system. And there are 2 indicators that people are looking for. which are the total variance and also the temporal autocorrelation that you do find here in the denominator. I'm just going to give examples. It's going to be clear, I think, with examples. So here I contrast two scenarios. These are time series that were generated with a simple ecological model of population dynamics. On the left, you have very low external variability. On the right, you have high external variability. And in both cases, the parameters defining the internal dynamics of the system are exactly the same. So in one case, you have very weak external forcing. In the other case, you have very strong external forcing. And so it's quite obvious in the two cases that you have one time series that has more variance than the other. And you see the impact that it has on the regression at the bottom. And you have the different quantities that are computed from these two time series. So in this case, you see that the total variance is much larger for the simulation on the right. The external variance is indeed much larger for the simulations that you have on the right. This is what we expected because that's how we generated the simulations. And you do see that the two measures of resilience are slightly different, but they are close to each other. They are different in this case just because of chance alone, just because of the simulations that I picked. It happens that the slopes of the regressions were slightly different from the other. But otherwise, everything should be the same given the conditions I ran those simulations. But here you have another example. So in these two time series, you have exactly the same amount of external forcing, but you don't have the same internal dynamics. So on the left, you have a system that has high resilience. So in this case, it's an ecological system. The density dependence is very high. In other words, the amount of competition you have between organisms is very high. So this should tend to stabilize the system very quickly. And on the right, you do have low density dependence. Things are taking much more time to settle. And it's quite clear from the two figures, from the two time series, that you do have different signatures in terms of two different statistical signatures of these dynamics. These are revealed by the autoregression that is performed and illustrated at the bottom. So on the left, you have a slope. As I said earlier, you have a slope that is much closer to zero than the one you have on the right. You also see that the amount of external variability is not the same, and that the spreading of the data is not the same also. It differs very significantly. So in this case, if you compute the different metrics that I talked about, the total variance is slightly larger on the left. This is unexpected. I think it's also just a matter of chance in this situation. Oh no, I guess it's also because I generated maybe by simulations larger external variance, because you see that it's much larger on the left than it is on the right. What is clear though, if you do compare the two figures, is that the amount of resilience that you do have in the two different systems is much, the resilience, the number itself is much larger on the right, which indicates that the resilience of that system on the right is much lower than the one on the left. Okay, so we're moving on. Now we have shown where these early warning signs for critical slowing down are coming. What's the original motivation for those? You have here, you can read that again eventually if you want to have the summary. But the key point I want to make at this stage is that most systems in reality are not isolated. So far, the theory has been developed and used only for univariate systems. So the reality in ecology, as I said, and in many other complex systems, is that you have a better representation with a network where you have a fairly large diversity of nodes and a large diversity of the types of interactions you do have among those nodes. And it's plausible that the univariate theory in this case is not appropriate to describe the stability and the resilience of those systems. And to prove that, I'm just going to take a very simple example. Now I ran simulations for two interacting variables. So one could presumably represent bacteria, and that you have the amount of bacteria that you have in a body, and the other being the amount of antibodies that are generated in response to the presence of the bacteria and that are acting against them. You can think also about a predator and a prey, how much they covary in an ecosystem. So in this situation, what's interesting is that what we previously thought would be external variabilities, external forcing, actually could be different elements that you do have in an interacting network. And so in this situation, if we just take the methodology that I talked about earlier, we may wrongly attribute the differences among the different components to differences in resilience. So in this simulation in particular, I simulated the lower trophic level. So the bacteria, I simulated it to be highly stochastic. So there's a lot of external forcing in the bacteria. But then I simulated antibodies that are reacting highly deterministically to the presence of those bacteria. So there's no external forcing whatsoever in the dynamics of the antibodies. In this case, they're just responding to the amount of bacteria there is in the system. And so if you decompose the variance, as I explained earlier, what you do find is at the end, a much larger variance for antibodies than for bacteria, which should not be the case because there's no external forcing in this simulation. It's just that the internal dynamics of the system itself that is taking place. And so we could wrongly compare the two and say that the antibodies are actually more variant and therefore they are less resilient. We also find that they do have external variance that is comparable in both cases, and a larger resilience for the bacteria, larger resilience for the antibodies, the number being closer to 1, which in this case is expected. The bottom line is that we may wrongly interpret those time series and say that the antibodies are not necessarily resilient, or they're subject to a lot of external forcing. And the reason why is that the antibodies, their own dynamics, are driven by the variation in the bacteria abundance, and we need to take that into account. So that's the special feature you have of multivariate systems in here. So in this situation, what is preferable to do is to run some kind of a multivariate autoregression model instead of a univariate as we did before. So in this situation, the state of the variable yi at a certain time is a function of the state of the variable itself at the previous time step and the reaction you have to that state, plus the reaction that you have to all other variables or interacting elements you have in the network at the previous time step, and then some external forcing. And so in this case, variation in the variable I is not only driven by its own internal dynamics and the external forcing. You can see from this model that it's also generated by variation in other elements that you do have in the network. So you can think in this case of a predator-prey system, for instance, where the number of foxes you have on Bylot Island is a response to the number of lemmings you had in the previous time steps. You can also think about the human body this way, and that's what we're going to look at with an example in a few slides down. You can look at many types of networks, their dynamics with such a multivariate autoregressive model. The nice thing is that we could rewrite this using matrix notation. So we're gonna run the multivariate autoregression for all of the different variables you do have in the system. And we're gonna collect all of the regression coefficients in a matrix that we'll call matrix A. That has some clear interpretation. All of the elements you have on the diagonal are called autocorrelation parameters. So these are basically parameters describing self-regulation. So how much a variable in a system regulates itself in response to its own state. And then you have cross-correlation parameters. So every other parameters that are off the diagonal that do describe the response, their response to other variables in the system. So these are basically all of the links that you do have in the network representing the interactions among the nodes. So now we have an autoregressive process that could be rewritten in matrix form. So you have the vector y times t plus little t that equals the product of J, the matrix J, and the vector y at times t, and you have a vector of externalities. In this situation here, J is just a diagonal matrix with some particularity. Its elements along the diagonal are the eigenvalues computed from the matrix A. And using basically the same algebra as above, I think it's not even shown above. Hold on. We get to stochastic resilience in a very similar formula to the one that we had before, with a very slight modification that is important for interpretation. So stochastic resilience, remember previously it was 1 divided by 1 minus the square of the regression coefficient. Now it's 1 over 1 minus the square of the eigenvalue corresponding to a given variable. And this eigenvalue obviously is influenced by all of the different coefficients, the structure you have in the matrix A. And so in this situation, the stochastic resilience, what it tells us is that the resilience for a certain variable in a system is not only driven by its own internal dynamics, but it's also driven by the dynamics of all of the other elements that you do have in that system. And basically, this is what I was telling earlier with the predator and prey example, or bacteria and antibodies. You have forcing that is happening by the external. You also have forcing that is happening because of changes in all of the other variables that you do have in the system that cause a certain change in one given variable. So this is just basically summarizing what I've said. In the multivariate system, not only external variability is taken into account, but also the variability that is propagated between its interacting elements. The bonus is that earlier we had some different statistical properties we could look at from time series that were all univariate. And once we reach a multivariate system, obviously we eventually get some measure of covariance that is also informative of the state, the system's dynamics. So the previous theory for univariate systems was telling us that an increase in the variance could be indicative of some slowing down of the system. While in here, what this equation tells us is that an increase in the covariance among interacting elements could also be informative of some permanent change happening to the dynamics of the system. So, in summary, for the theory, autoregression coefficients, they determine the resilience of the system. We need to look at autocorrelation and also cross-correlation coefficients. As the systems goes down, both of them will eventually go up. So the autocorrelation will get closer to 1, and the cross-correlations, they could either be negative or positive, but they will go away from a 0 value. They will be stronger. So the absolute of the cross-correlation should increase. And this leads to 2 predictions. So the variance will increase with slowing down, and the covariance will increase with slowing down as well. So now it's time to explore those with a real case. So the original question that motivated all of the development of this theory was, is there any evidence of some slowing down before you have a meltdown of a physiological system? So basically, in our case, we were interested in human health and aging. Our original question was, as people age, do we eventually get slower? So is there evidence that the different elements interacting in the physiological system are just acting more and more slowly and responding more slowly to externalities, which could eventually bring them to states that are very harmful or potentially lethal. Unfortunately, the data that we had in the hands was not about aging. It was rather about hemodialysis. So we were looking for highly detailed, high resolution time series for a fairly long time series for patients that had eventually some major change in their health. So the data that we found, unfortunately, we wish it was about aging, but we were not able to get our hands on such type of data. But instead, we had data for people that were subject to hemodialysis. We had patients that were followed every 2 weeks for at least 1 year, and then some of them for many more than 1 year. In the analysis that I will present, we restricted ourselves to the year, to a single year. And all of those patients were followed until eventually they unfortunately died from different causes. As I said, we had data on time series with blood markers taken every 12 to 16 days. So it was an average of 14 days. And there were 10 different blood markers that were recorded at each time blood were sampled. Unfortunately, I'm not the human physiologist here, so I could not say much about those blood markers, but apparently these are used very regularly by practitioners to make diagnostic on the state of those patients. What I was also told by the doctor working with us on this project is that usually people, they look at single markers to detect potentially problems in health, and instead of looking at the whole suite of markers. And so the originality here is partly to look at the entire range of markers and how they do interact with them. And also people just look at the average of those markers, and not necessarily, so people look for change in the average of the markers over time to anticipate physiological meltdown. In our case here, we will look at the variance over time, and not only the variance, but also the covariances among the different blood markers. I will skip the basic figures showing how the variances and the covariances are changing over time. Simply, it was a simple problem. I did not have those figures when I made the talk yesterday, but I could tell you that the most markers, their variance increase prior to death, something like 25 days before death eventually happens. And the covariances also have increased prior to death. And these were just the primary observations that we've made that motivated the further analysis and the development of the theory, because we wanted to have a better understanding of what's actually going on and what's driving those major changes in those blood markers. None of them, however, change in average. So the blood markers themselves were not, if we were just taking the average of those blood markers over time, they were not sufficient to make any diagnostic about death that is approaching. However, as I said, the variances and the covariances among the markers very, very significantly change, something like 25 days before death happened. So here's just one example of a time series that we took. So you have platelets and white blood cells they do vary over time. All values were standardized, so they are scaled. While their average is of 0, and the total variance is 1, and the variance may be non-stationary in that it could increase or decrease or stay the same as time goes. And so what we did is that, as I shown earlier, we did the multivariate autoregression for all of the different blood markers. Here you have an illustration of some of them. You have MCV on the left and platelets against the RBC on the right. So on the left, you can see that the autoregression coefficient, so this is a single blood marker against itself. The slope is pretty clearly close to 1. And so it has very high temporal autocorrelation, and it has a fairly high also residual variation around it, suggesting that there's a lot of variability driving, external variability driving the system. On the right, you have the cross correlation, and here the cross correlation is different, significantly different from 0, indicating that the two are reacting to each other. I think the red line is just representing, well, I don't even remember, that might be an error. The red line is not appropriate. It shouldn't appear here, as the regression is negative. Anyway, the bottom line is that we started to explore this multivariate autoregression, but the thing is that we were anticipating changes in the dynamics of the system to happen over time. And so we could not restrict ourselves to a single multivariate autoregressive model. Instead, we needed to have a non-stationary model. And so what we did is that we made a time dependence on all of the regression coefficients. And we also made a time dependence on all of the residuals, so that we could allow those coefficients to change prior to death, and the residuals as well. Everything was fitted by maximum likelihood. And at the end, we collected coefficients from the regression and from the residuals at any point in time to compute the different quantities I was talking about earlier. And we also did some model comparison to make sure that everything was statistically sound. So I'm just going to present some of the basic results we got from there. Here you have the average stochastic resilience for the different markers indicated by the red line. You have the value for each of the markers in black. And on the x-axis is the time before death in days. So at 0, it's the time the patient died. And the rest is the 1 year before death. And so in this case, we clearly see that the resilience of the system very, very significantly drops somewhere around 30 days before the patient eventually died. Keep in mind that it's a log scale that you have on the y-axis. So it's a very, very abrupt change in the amount of stochastic resilience we have in that system. So there's evidence pretty clearly here that there's a critical slowing down, explaining the observations that we made earlier about the increasing variance and the increasing covariances in the different markers. We also look at the amount of external forcing, having in mind that maybe, when people are close to death, it may happen because they're more susceptible to infections or some externalities changing their health. And so we do see indeed a certain increase of external forcing on average, but it's not that much. You can see from the different lines that some blood markers do have a much larger residual variation close to death, but otherwise some are not reacting or even reacting the other way around. And then after, we could also eventually look at the cross correlation and the autocorrelation, and all this goes pretty much in the same direction, although there are some markers that respond very, very differently. So on average, you have an increase in the temporal autocorrelation, so indicating that the amount of self-regulation in the system is decreasing, the system is slower, as the patients approach death, and the cross correlation coefficients also very significantly change, which indicate that basically the variation in one marker in the system could trigger some variation in other markers and generate variability and eventually push the system out of its safety zone. So take home from this is that sudden changes in variances and covariances prior to death are happening. This may eventually be used as a criteria for diagnostics and anticipate massive or very abrupt change in the health status. All evidence is indicating that there's some slowing down of the system, so it's driven by a change in the internal dynamics of the system, and not only driven by a change in the external pressure it experiences. And it's also partly due to resistance, but to a certain extent, because there's rather a massive drop in resilience. And well, that just repeats what I've said. So it's 3:35. I'd like to take just 5 minutes to have you think about this simple question, and then I'd like you to think to talk about it. Give me some of your answers, because now I'll switch to ecology back again, and we'll talk about the stability of very simple versus complex, more complex systems. What to expect, and eventually how this could translate in some new knowledge that could be used to understand human health and the types of things that I just presented. So we're just going to take a small break of a couple of minutes, and I'd like you to think and give me some intuition about this question, our complex systems. So by complex systems, in this case, I will have in mind the number of nodes you have in a network, the diversity of the types of links you have among these nodes, and perhaps the diversity and the strength of the links they are between those nodes in the network. So do you expect a more complex system to be more stable or less stable than a very simple one? Is anyone ready to give an answer, an ID? Does anyone has an intuition about the stability of simple versus complex systems?
I don't know if you can see the chat, Dominique, but there's two answers already. One by
Perhaps you can
Alice and one by Alice and
read
Rob.
them to me, because I have my screen share, so it's.
Yeah, so Alice said, I don't think the number of nodes matters necessarily, but diversity in node attributes and ties can make a system more resilient because it can break symmetries in the dynamics and thereby open up more ways in which a system can mitigate perturbations.
Yeah.
Likewise, Ellison said, yes, my vote is for more stable. And Patricia said also, I expect complex systems to be more stable than simple ones over the long term because of increased feedback loops that allow for better adaptability. And Grace is approving with all of that, also thinking that complex systems have the potential for more redundancy. And I will also say, what I was thinking is, it's actually one of my favorite measure of poverty versus richness is the diversity of alternatives. Thinking about how adaptive you can be. So if your car breaks down, do you have other ways to get to work? And that's a great measure of how stable an economy or a population might be. So I think generally there's a great consensus that more complexity should mean more stability.
Okay, just for fun, I haven't thought about using the poll when I was doing my slides, but now that we have that feature that is very easy to set, I'd like to do a poll and ask how many people think that more complex networks are more stable versus the ones that they do think that more complex networks are less stable.
Okay.
And while Juniper does that, do you have time for a question about the previous material you presented?
Yeah, yes.
I was curious because you said, like, unfortunately that you couldn't get data on aging, and then you use this dialysis data, but I don't know what possible data, what's the best possible data on aging, and I guess I'm not sure what aging is and how we measure it.
Well, that's a critical question, and indirectly that's where we aim to go. Actually, we want to develop measures of aging that are based on the system dynamics instead of using the biological or the chronological age. It's a whole field. There's thousands of people working around the world trying to find a good way to measure age in a way that is significant for healthcare. Because it's quite obvious that biological chronological age is not appropriate.
Okay.
Okay, well, that's funny.
Is everyone seeing the results, or just the host?
Just the host.
Okay.
So it's
Don't spoil it yet.
It's ongoing. So you see the people are voting right now.
21 votes in.
Will anyone contest the results?
I don't need to stay up all night watching that again.
People north of the border are not allowed to make fun of what's going on here.
Yes, it's too painful.
Okay, I think after 64% of people voted, there's 80% of people that think that complex networks are more stable, and 20% are do think that they are simple networks are more stable. So I mean that's corresponding very okay. Trying to get back at my slides, but I have this. It's a bit annoying. Is it possible to remove the poll, or am I stuck with it? Do you still?
I think it should be done.
Yeah, maybe you can close it.
Yeah, we'll have to close the share and take it again for some reason.
Mm. Mm.
Hold on. Why is that screen showing up? Do you have my slides or you have my internet?
We have your slides.
Have your slides.
Okay. Fucked up for a moment and then it got back. Okay. So that's a very old question in ecology. It dates to the mid 20th century, where very famous ecologists like Odum and MacArthur proposed that complex systems would be more stable for the basic reason that was expressed earlier. So basically, the more diversified it is, the more opportunities there are for perturbations to spread out and eventually be buffered by the different components in the system. Yeah, so you have the citation from MacArthur basically telling that at the bottom of the slide. But then came Robert May in early, well, Yeah, early 70s. So Robert May was he's archetypical of a complex system scientist, way before we started to call this complex science. He was coming from physics and got interested in many things in biology, including the stability of, and the dynamics of ecosystems, but also by epidemiology. I think he's one of the first, if not, well, he's among the first to have published and work on using epidemiological models. And he was very insightful in several of his contributions, and one of them was his famous book that was published in 1972, I think, which is called Stability and Complexity in Model Ecosystems. And he's really the first one to tackle this problem of complexity, diversity, and stability. So basically, he started the field, he pioneered the field of random matrix theory. He studied the properties of random Jacobian matrices. So you have one illustrated on the right. So here, just with plus and minus signs, describing all of the interactions. So a Jacobian matrix, for those that are not familiar with them, are basically describing the dynamics of every variable in a system in response to a small change in any other variable of the system. And the Jacobian collectively, there's some way that you can boil all of this information into a single quantity that will tells you about the dynamics and the stability of the system. And so Robert May was among the first to really formalize the problem of complexity and stability, and ask rigorously, what's the expectation? And so his proposition led to some criteria for local stability of complex random ecosystems. And here the word random is quite important in that all of the components in the Jacobian are drawn at random, and he studies the statistical properties of those matrices generated by a stochastic process. So basically, he found that you can essentially describe the characteristic of a Jacobian matrix with four quantities that eventually will set constraints on stability. So you have alpha, which is the some measure of the strength of the interactions you have. So you have the Jacobian on the right. Some elements are null and some elements are non-null, and the alpha is describing how different from zero these non-null elements are. So the larger is alpha, the larger are these coefficients of the null elements. S is the size of the network, C is its connectance, and D is the average of the elements that you do have along the diagonal. So it's describing self-regulation, density dependence. And what Robert May found is that for such random ecosystems, there's some bound on stability that is driven by the amount of complexity that you do have. So basically, for a system to be stable, it has to respect the equation that you have on the top left. So the product of alpha and the square root of S and C must be smaller than self-regulation. This is slightly better explained or visualized with this figure about what people call a Greshgorian disk. I have trouble saying that. It's basically a disk representing the distribution of eigenvalues for such Jacobian matrix. The position of the center of that disk is given by the average of the diagonal elements, and the radius of that disk is given by the product of alpha and the square root of S and C. And so the larger is, so the more diverse, the more connected, or the stronger are the interactions in the system, the larger will be the radius. And the position of the circle itself is depending on the amount of self-regulation you do have. And the system becomes unstable once the largest eigenvalue, given by the red line, is crossing the value of zero for the real part of the eigenvalues. So this theory is telling us that basically the more complex So the more diversified or stronger our interactions, the less likely the system is to be stable. So complex systems are less stable than simple ones, according to this theory. And people have been challenging this idea in ecology for now about 50 years because it's completely counterintuitive, and um, and the poll is just confirming what people have been thinking for years in ecology. The reason why it happens, there's not much work explaining why this is expected to happen, but my own interpretation, and we could come back to that later, but I think it's the reverse of one thing that was said earlier, is that the more interactions you have in a system, the more you have feedback loops that are taking a very bizarre route, and instead of stabilizing the system, they could eventually amplify perturbations, and those amplifications could eventually go back at the original variable that was disturbed, and since the perturbation is now amplified, then it will grow and grow and grow, and the system will become eventually unstable. So that relates to what I've shown earlier with the multivariate systems and the interpretation of the regression coefficients that we have. So one thing that we did, we wanted to test empirically this prediction about the complexity stability relationship with real data in ecology. So one thing that we did is that we looked for literature, and we managed to pick up roughly 120 different ecosystem models that were describing the dynamics of the different species in those ecosystems. We converted all of those models into Jacobian matrices, and then looked at their statistical property, and also looked at their dominant eigenvalue to see if they were more stable or less stable according to their statistical properties. So first thing we found is that actually there's no such thing as a relationship in real ecosystem between any measure related to complexity and the dominant eigenvalue. So on the y-axis here, you have the real part of the leading eigenvalue that was standardized. We removed the effect of the diagonal elements. And on the x-axis, you have the number of nodes, so S, the connectance, the average interaction strength, the sigma, and all of these together, plugged together at the bottom right. So there's no relationship between any of them. The different colors, by the way, they do correspond to different ecosystem types. So you have marine, aquatic, freshwater, and terrestrial ecosystems, and none of them is their complexity is related to their stability. So we pushed the question a little bit further, and one thing we observed is that actually there was one reality that was not looked at all in original MACE theory, which is that for complex systems to exist, you need to have smaller, weaker interaction strength. So the more diverse and the more connected the system is, the smaller will be the average interaction strength among them. And presumably, the larger will be the diversity as well of the interactions that you do have among them. So that relates partly to one hypothesis that was raised earlier prior to the poll. I think I will skip those two figures. Don't want to go too much into details, but I'd be happy to talk about them further. But just to say that one thing we did is that we tried to look for properties that were driving this absence of relationship that was expected between the complexity and the stability. And actually, we found that many non-random features of real networks are contributing to the stability of the system. But unfortunately, we could not predict the stability of any system based on one or a few of those probably of those properties. So we're still in the dark. We don't have the proper metric to summarize the information there is in Jacobian matrices to be able to predict the amount of stability that you do have in a system. So now what we do is that we're trying to use this theory to inform the work we've been doing previously with aging in order to make eventually some predictions about what to expect with aging about the dynamics and the structure of interacting networks happening in physiological systems. And that pretty much covers what I had in mind, but I just want to conclude with one single question that eventually popped to me when I was doing this work with Alan. And I think it's a very interesting question that could be easily tackled within the workshop. It's one that requires fairly simple simulation models, but that could lead to a lot of interesting follow-up observations. So at first, I presented a study that looked at the properties and the stability of a system where natural selection optimized the functioning of that system as a whole. So the human body has been shaped by millions of years of evolution in order to respond and react to external disturbances like infections, viruses, bacteria, and injuries, and so on. So the body itself is a network that is optimized for its overall functioning, its whole functioning. So the emerging properties are optimized by natural selection. This is in very stark contrast with an ecological network where we know that natural selection acts on the nodes themselves and not the properties of the whole. That will eventually lead to some properties of the whole. So natural systems are also stable, but not because natural selection happened to play on the functioning of the entire piece, but rather because it just generated these emerging properties from selection on the individual nodes. And so my question at this point is, do we expect different networks given that natural selection is operating on the stability and on selection of properties at different levels of organizations in those networks? That's it for today. I'm happy to take questions.
I had a question.
Before you get started with questions, can everybody unmute themselves and give Dominic a big round of applause? Woo!
You can go ahead, Nicholas.
Great, thank you. Thank you for the talk. It was very cool. My question was, when you were talking about the Kirschgården circle theorem with random matrix theory, I haven't actually dug into this literature myself, but I remember reading about some papers that are getting published associated with random matrix theory and like third order phase transitions. And a lot of times I've been seeing people try and connect that back to some structure of ecological systems because of kind of the very thing you were saying, this debate between our intuition and what Bob May showed pretty early on with these simpler complex systems. But when we're introducing this additional structure or relationships into systems, it also oftentimes generates these third order phase transitions, which changes their dynamical behavior, in particular, like their stability and resilience. Are you familiar with that at all? It also may be the case that, like I said, I haven't spent a ton of time digging into it, so I may have misconstrued some of the work.
No, well, I am with the phase transition you're referring to, I'm not that familiar with. I never heard about that, but maybe I did work, and some others did work on some aspects that are touching on this. I know that there's one quite fundamental paper that came in around 2012, where they started to look at other statistical properties of the Jacobian and see how much they impact eventually the leading eigenvalue. And one of the things that was pushed forward and it was found is that having correlations within elements. So if you just flip the matrix and you look at correlations among pairs of elements, this could very significantly impact the shape of the disk. So to make things more concrete, having predator-prey interactions where you have a match between positive and negative interactions tend to stabilize systems. When you have some positive correlations, but among negative elements. So in this case, this corresponds to competition. So we have minus and minus matches of the coefficients in the distribution in the Jacobian. That's even stabilizing the system further. And at the opposite, when you have mutualism, so plus and plus matches, that generates feedback loops that tends to destabilize the system. So that's one of the things that has been found in early 2010s. And then after myself, with a colleague and friends, we started to look at spatially structured ecosystems. So imagine that you have a lake and a forest, and some animals are moving between the two, and so they're connecting the lake and the forest because of dispersal or because of foraging, for instance. That generates a very particular types of Jacobian matrix when you're looking at the stability of the, or at the dynamics of the entire meta ecosystems, because you basically have the forest where you have most of the species interacting with each other. You have the lake with most of the species interacting with each other, and then you have, so that makes two blocks in the Jacobian, and then off those blocks you have sometimes some non-null elements that are corresponding to movement or dispersal. And having this block structure tends to stabilize the dynamics as well. That's one of the things that we found.
Cool. Thank you.
Other questions?
There was a question earlier in the chat. I don't remember who it was, but I think folks were curious about how exactly, when you have data and you try to measure stochastic resilience, how you do the regression. Do you remove outliers? Do you do regularization? And I was also curious about this, especially like, how would you know if your temporal resolution was wrong? And is it possible that you might need different temporal resolution for different elements in a multivariate system?
Well, that's an excellent question. The one about temporal resolution. I could start first by answering how I did the regression, and then after moving to this. So regression is you're just modeling the state of the variable at times y at so the state of the variable y at times t plus delta t is a function of the state of all the variables at previous time step. And the standard theory is linear, and so you're just using linear regression coefficients. And then the distribution of residuals, you can pick which one you want. So in our case, all of the data were normally distributed, and so we just use a normal distribution. But if for whatever reason there were outliers and we needed to have a different distribution, that would have been possible to do it. It's just that you're not doing it with standard linear model fitting. And in our case, it was a bit more complicated because all of those things were not non-stationary. And so we need to have time dependence. And so we had parameters expressing how the time dependence is changing. So basically we had to deal with minimal value, maximal value, and the rate of change and the point of inflection of that change. So these were parameters we had to evaluate. So that answered the first part of the question related to distribution. So you just play, because it's maximum likelihood, it's fairly easy to pick whatever distribution you want you need to. The only thing is that if you want to perform the matrix algebra part of the analysis, then you need to have a linear model. That's the minimal requirement. And I mean, this is quite standard anyway in stability analysis to do a linear approximation. So all of the conclusions should be taken with some reserves, some care, because they're done in the neighborhood of the equilibrium, and they're not necessarily it could not be extended necessarily to large disturbances far from the equilibrium. For the second thing, this is a question that is highly relevant, the one about time resolution, but unfortunately we didn't have the data to look at finer time resolution. I wish we had daily blood samples, for instance, and we could eventually explore different time gaps and see how much it influences the results, and finding the sweet spot at the scale at which we should make the observations to detect those early warning signs. I'm honest, I still ask myself if we've been lucky, and it's just that the data are that way, and we got that answer. The story is fine so far, but it may be just this particular data set that has this story. But if we look across different data sets we're playing with, there are other data sets we started to work on that are not as intensive as this one. So we could not do the multivariate autoregressive models, but nonetheless, we could look at time changes in total variance and covariances, and we see that happening over and over again. So it's, to a certain extent, it's reassuring that it's not something that we found just by luck.
Well, and I was also curious because the results could be even better in some way, because the biomarkers that don't show sign of any slowing down could just be because the time resolution is not right for those biomarkers. And
Yeah, of course. A good example, imagine that we have recorded not only the biomarkers, but we took blood pressure and heart rate on those patients at 14 days interval. I mean, we know that the blood pressure and the heart rate will change if some is just standing up all of a sudden. Heart rate will go up, blood pressure will increase, and this is a very, very fast reaction that would certainly not be picked up with a time interval of 14 days. And so we need proper time intervals to be able to detect those early warning signs.
I was going to say that I think wearables are very big or getting very big now, and that would be a rich source of data probably. Not necessarily just the standard iWatch or whatever, but I think there's a lot of research and development to do.
Yeah, we've thought about that, and yeah, we're still looking for some with aging, because it would be wonderful if we could be able to indirectly age people based on the system's dynamics and not their chronological age.
Any other questions from the audience?
Yeah, sort of along these lines. Have you ever played with a menopause data set in either humans or other animals? Or I'm thinking of like wolf and dog aging molecular data sets that I think might be public, but I don't know if you've looked into those. It seems like menopause in particular is maybe an evolutionary solution to maximizing reproduction and survival in this sort of fitness game. And then wolves and dogs, I think, fall on this side of the spectrum where they age really quickly because they invest, I think, more in reproduction at the cost of.
Yeah, that's a very interesting line of thought. That's a good one. Would you look at blood markers or?
Yeah, I think so. I think work has been done, but I don't know if they looked at like actual networks of gene expression. So I think the people who did this work, I think it was Bridget von Holtzlab at Princeton, who does a lot of dog and wolf molecular work. And they did gene expression from blood of individuals of different ages. But yeah, that could be a really neat data set, because if they might show this sort of more rapid decline than humans do. Yeah. I don't know.
One thing we thought about as well is we were wondering if with the massive number of studies that are ongoing with the COVID, if we thought about using the studying the dynamics of the immune system as well. And so if we had very regular blood samples with distribution of the different antibodies at high resolution, I mean, part of what is happening is definitely a collapse of the immune system with the COVID. And so perhaps we could eventually detect this happening before it's too late, because otherwise it's very, very difficult to characterize. And so we thought about that, but it would require very, very high resolution time series, something like samples taking every few hours or something like that for patients that have been sick. An alternative that would be interesting as well is having such time series, but for people that get the vaccine, so that you can track their response and the reaction of the body to this shock of the vaccine. We'll have to look at it.
Yeah, it's really cool to think about. Thanks for the talk.
Thanks.
I enjoyed it.
So we can continue the discussion. I know we're sort of running out of time a little bit, but so if anybody needs to hop off for a human break, they can. But if anyone wants to stick around and if you have more time, then we can keep
Actually, I unfortunately I have some commitment as well.
Okay. Then
but
we can
but
continue the
I could.
conversation on Slack to sort of asynchronously as after.
Yeah.
Okay.
Yeah, there were some really good points just being made in the chat right now, so we can keep the conversation on Slack.
Or I'd be happy to eventually join. Tomorrow it's going to be a bit complicated for me. I just saw that university may be partly open next week. So I may be able to connect at the university, and during those free time breaks, I would be very happy to join and follow up on those questions.
Good.
That'd be awesome.
Mm.
All right, let's thank our speaker one more time.
Merci.
Thank you, Dominique.
Pleasure.
Always good to see you, Dominique, and thank you so much.
Pleasure, and hopefully we'll
Yes.
see us in real in soon.
Yeah, I know, it's so sad. You're so close in space, but so far away. Oy.
Okay, good. Well, have a good afternoon.
You
Ciao.
too.
Bye, Dominique. Thank you.
Bye.
Bye.